my master's work at Cornell University, and really gave me my first exposure to recirculation aquaculture technology. And he's been a good mentor over the years for me as well. So today we're going to talk a little bit about circular tank design, fish culture tank design. We're going to key in on circular tanks and talk about all of the design elements associated with circular tanks and how they can be used in aquaculture. So we're first going to talk a little bit about density and feeding rates and feed loads. We started some of that already in the last two, and I think this is a good follow-up on some of what we just spoke about, but not quite as detailed as the previous two slide presenters. Then we're going to go right into the Cornell dual drain technology, and this is technology that was developed at Cornell University. And a lot of the research on it was done at the Freshwater Institute. So we'll talk some about that and how this technology can be applied to partial reuse aquaculture systems, recirculated aquaculture systems, and even single pass flow-through systems as well. We're going to talk about the critical design elements, which are the inlet and outlet structures, as well as the center drains as well. And we'll talk about some of the features like mort removal, lighting, and population management within these systems, and how the tanks can be designed to support those. And really all of this is really to drive good water quality in the tanks, survival and growth, increase or improve the health of the fish and reduce the stress of the fish, get good feed conversion ratios, uniformity of the fish, in the end, good fish condition, and to be profitable in the end. So you've heard a little bit about feed loads today and densities and feeding rates. This graph sort of represents how they're all related to each other. A lot of people know what their feeding rates are in percent biomass per day at any point during their production cycle, and they understand what their densities are. But the feed load is really a function of both of those put together, and it's important to understand that. So the feed load is represented by kilograms of feed per cubic meter of culture volume per day. And it's a function of the culture density in kilograms of biomass per cubic meter times the feeding rate in percent biomass per day. And that gives you your feed load. And we heard a range of 0 to 1.5 maybe. I probably would stay below 1 in most cases, but this graph represents the different feed loads here, 0.2, 0.4, 0.6, 0.8, all the way up to 1.2, at different culture densities and feeding rates. So if you take that 0.6, for example, and you follow that yellow curve, if you have a product that requires 6% biomass per day feeding rate, then you need to manage a density that's down around 10 kilograms per cubic meter to achieve that. So that's just important to understand, and that feed load really drives all those mass balances that Mike Timmons was talking about. And the mass balances in the end drive the recirculation rates and the turnover rates. So this is another graph that just represents the turnover rates based on your feed load in a system. And this is very general. It's based on a max TAN of 1.8 milligrams per liter, and it represents a partial reuse aquaculture system. So the new water coming in here, this is makeup flow water here. It's based off of that max TAN rate, and new water coming in at about 0. So a differential of about 1.8 of new water coming in and water leaving the system. The recirculation rate here is based strictly on the mass balance for oxygen, and it's related to a deficit across the tank of about 8 milligrams per liter. So that means if you're maintaining, let's say, 8 milligrams per liter in your tank, then your inlet needs to be about 16 milligrams per liter. And this is the relationship between turnover rates and feed loads based on those inputs there. So you'll see that turnover rates, this is in tank exchanges per hour. So if you have a low feed load, you require a relatively low turnover rate. But as your feed load increases, these turnover rates get higher and higher. And so if we again look at that 0.6 there, it's showing a turnover rate for makeup water a little over a half a turnover per hour, and the turnover rate for the recirculated water at a little less than 2 turnovers per hour, with a total of about 2.5 turnovers per hour for that tank. And these represent a reuse rate of 75% across the board. Reuse rate is the amount of water that's recirculated compared to the amount of water that's exchanged in new water in a partial reuse aquaculture system. So just a slide to sort of bring all that together and demonstrate how those are all related to each other, and show how that impacts the turnover rate of the tank, because the turnover rate of the tank is really critical when it comes to your tank design. So how do you do that? How do you plan for that when you're planning out your system, when you're working on your bio program and things like that? And these are some of the steps that I work through, and I apologize for this small graphs here. I was expecting a larger screen, I guess. But so the first step really is to predict that growth rate for your fish. And you just saw this slide from Mike: linear growth and growth for length, and exponential growth for weight. And we're really going to focus on the weight growth here. If you take that growth rate, you can convert it to a percentage biomass per day, growth rate in percentage biomass per day. If you take that and you multiply that times a feed conversion ratio, which I have here starting at 1, going up to 1.2-ish, then you can calculate the feeding rate in percent biomass per day. If you know your feeding rate, so this feeding rate is represented by this chart over here. So it starts at about 3% biomass per day and drops down to about 1% biomass per day at the end of that production cycle. So if you take that feeding rate, you can take the feed load, and what I try to do is determine a relatively steady feed load. So this blue line here represents a feed load that's going from about, I think, 0.6 to 0.7 here. And then that will calculate your density that the fish need to be maintained throughout the whole growth cycle of that product. So it's a good way to just sort of chart out what your density, your feed loads, and your growth rates are going to be throughout the whole growth cycle. That will determine your turnover rates for your tank. If you maintain a relatively stable feed load, your turnover rates for your tank should be relatively similar in nature. And it really tells you how much fish you can put in a tank at any given stage of that fish's life. And these two graphs, one has a high feed load, 0.6 to 0.7, which results in a density of around 20 up to 70 kilograms per cubic meter. And if you drop that feed load to 0.4 to 0.5, then you start about 10 kilograms per cubic meter and go up to about 50 kilograms per cubic meter. So just to sort of bring all that together for you guys. So that turnover rate, again, is really important to tank design. We're going to focus on Cornell dual tank technology. There's a couple of references that you can look up to get more details on this. But it's really driven by three primary factors, three primary tank properties. One is the tank inlet structure, the bottom drain, and the side drain outlet. So dual drain really represents two different drains out of the tank. One is the center drain and one is the side drain. And the tank inlet over here is also part of that. So what we're trying to do with dual drain technology is provide the right environment for the fish in the tanks, provide the right swimming speed. So this is very applicable to salmonids, trout and salmon culture. But we're also trying to manage the solids in the tank and remove the solids from the tank quickly and provide a really nice, well-mixed environment for those fish. So some critical design elements for the inlet structure is it can be internal or it can be external to the tank in some cases. And it really needs to be adjustable for flow rates. The nozzle exit velocity needs to be adjustable, and the orientation of that